Okay, let's talk about the master switch for every single voluntary movement you make. From blinking your eyes to taking a breath, it all comes down to the neuromuscular junction. Now, for your exams, just knowing what it is, that's not going to cut it. You need to know how to hijack it, how to shut it down completely, and most importantly, how to safely turn it all back on again. Let's dive in.
So, here's our roadmap. We're going to start by hijacking the signal before it's even sent. Then, we'll get to the main event and meet the two major types of drugs that do the blocking. We'll look at the ones that compete and the one that's a clever imposter. After that, we'll talk clinical reality, why we use these drugs and what can go horribly wrong. And finally, we'll cover how to get everything back under control.
Right, so before that signal can even get to the muscle, there are a bunch of ways we can interfere. Think of this as presynaptic sabotage. We're cutting the wires before the switch can even be flipped. So here's the normal sequence of events, step by step. First, you get the raw material, choline, into the neuron. Second, you make acetylcholine and pack it up into little vesicles. Third, the action potential zips down and arrives. And fourth, the vesicles merge with the membrane and release their cargo. It's a really elegant system. And, every single one of those steps is a potential target. So, how do we mess with this process? Well, we can stop the choline from even getting in with something called hemicholinolium. We can prevent the acetylcholine from being packaged with fosamicol. We can even stop the action potential from ever arriving using local anesthetics. But the most targeted attack is on the release mechanism itself. And that brings us to a very famous toxin.
Yeah, this is the perfect example of taking a deadly poison and turning it into a super precise clinical tool. What botulinum toxin does is it literally snips the proteins, the little molecular ropes that pull the vesicles to the membrane. So if there's no fusion, there's no signal release and absolutely no contraction. It's an incredibly specific mechanism that we now use for everything from cosmetics to controlling severe muscle spasms.
All right, let's leave the presynaptic side of things and move to the main event, the postsynaptic receptor. This is where the real workhorse drugs for clinical paralysis get the job done, and they use two totally different strategies to achieve the same goal.
Pay attention here because this slide is absolutely crucial for your exams. The difference is simple, but you have to know it. Non-depolarizing blockers are just straightforward competitors. Think of them as the wrong key in the lock. They fit, but they can't turn it, and they stop the real key from getting in. Depolarizing blockers, though, are sneakier. They're like a key that fits, turns, and then breaks off in the lock, jamming the whole mechanism open until it just gives up and shuts down.
So, first up, let's talk about the competitors, the non-depolarizing agents. These are the true antagonists. They're going head-to-head with acetylcholine, fighting for that binding spot on the nicotinic receptor.
This table breaks down the main families you really need to know. Yeah, they're grouped by their chemical structure, the benzyl isoquinolines and the ammonium steroids. But let's be honest, clinically, what really matters is how long they last. The whole game is about timing, so picking the right drug for the right procedure is all about its duration of action.
And here's a great clinical pearl for you. You might think you need to block 100% of the receptors to get the job done, but you don't. The body has this built-in safety margin. So once you occupy about 70 to 80% of them, you've achieved effective clinical paralysis.
Now, this sequence is a classic exam question, so make sure you've got this down. The paralysis spreads in a really predictable way. It starts with the small, fast-moving muscles of the face and neck, then moves to the limbs, and finally it hits the diaphragm and respiratory muscles. And guess what? Recovery happens in the exact reverse order. Just remember this. Respiratory muscles are the last to go down and the first to come back online.
Okay, now for the odd one out, the great imposter, succinylcholine. This drug looks so much like acetylcholine that it completely fools the receptor, but with very, very different consequences.
Its structure really tells the entire story. I mean, look at it. It's basically two acetylcholine molecules just fused together. So what does that mean? It means it binds to the receptor perfectly and it activates it, but it's resistant to the enzyme acetylcholinesterase that's supposed to break it down. This two-phase block is a super high-yield concept. Phase 1 is all about depolarization. You see those classic muscle twitches, the fasciculations, as all the receptors fire at once. That's followed by paralysis. But in phase 2, if the drug sticks around, the receptor just gets overwhelmed. It burns out and becomes desensitized. At that point, it won't respond to anything, not even the real acetylcholine.
And here is the absolute critical difference you have to remember. The duration of succinylcholine has nothing to do with what's happening in the synapse. It's broken down by an enzyme floating around in the blood plasma called butyrylcholinesterase. And that's why its effects can vary so much from person to person, depending on their genetics and liver function.
So we've got these incredibly powerful pharmacological tools. Let's bring this all to the bedside. When do we actually use them, and what are the life-threatening dangers we have to look out for? As you can see, their uses are really broad and, frankly, essential. They give surgeons a perfectly still field to work in, they make intubation possible, and they prevent violent muscle contractions in situations like tetanus or during electroconvulsive therapy. I mean, this level of muscular control is really a cornerstone of modern medicine. Okay, this is your toxicology checklist. Respiratory paralysis is the obvious #1 danger, right? But you also have to be watching for cardiovascular effects, histamine release, and especially with succinylcholine, a life-threatening spike in potassium as it pours out of those depolarized muscle cells. And all that leads us to the most feared complication of all. Malignant hyperthermia. You have to know this. This is a true lights and sirens medical emergency. It's a rare genetic condition where if you give a patient succinylcholine or certain anesthetics, their muscles go into this crazy hypermetabolic overdrive. Calcium gets dumped everywhere, leading to intense rigidity and a catastrophic spike in body temperature. So we've successfully flipped that master switch to off, but the job isn't over until we can safely and reliably flip it back to on. The reversal strategy is every bit as important as the block itself. And the reversal has to be perfectly matched to the drug you used. For a standard non-depolarizing block, the plan is simple. We flood the synapse with acetylcholine using an inhibitor like neostigmine, so the real stuff outcompetes the blocker. For the steroid-based drugs, we have an even cooler solution, sugammadex, which is like a molecular sponge that just soaks the drug right up. But for succinylcholine, there is no reversal agent. You just have to wait. And for that terrifying emergency, malignant hyperthermia, the antidote is dantrolene, which directly stops that massive calcium release in its tracks. And this table right here brings it all home. Seriously, this is your study guide on a single slide. It lays out what's normal versus the 2 types of block, and exactly how you reverse each one. If you can walk through this table and explain every box, you're absolutely ready for your exams on this topic. So let's end on a more profound thought. Back in 1947, an anesthesiologist named Scott Smith actually injected himself with a paralyzing agent as an experiment. He was completely unable to move a muscle, couldn't even breathe on his own, yet he remained totally conscious and aware of everything happening around him. The fact that we can pharmacologically sever the mind from the body's motor system, it's just a powerful clinical reality, and it really makes you think about how fundamentally separate our consciousness is from the physical machine that it pilots.